Okay, let's discuss the trace of a matrix. Okay. So the trace is the sum of the diagonal entries. So if you have A is equal to, the usual A11, A12, all the way out to A1n and A21, A22, and go all the way out to AN1, and we go all the way out to A and N. Okay, so if you have this, well, the trace of A is just going to be A11 plus A22 plus A33 plus all the way out to plus A and N. Okay, and now this is also going to can be expressed as I equals 1 through N. Okay, so the trace is doesn't care about the transpose. So if you take A and its transpose, well, you can take the trace and you can swap these guys around and nothing happens. Okay, and the trace also doesn't care about the order in which you multiply two matrices, just two. If you multiply more, then you need to pay attention. Okay, which is what I'm going to go over here. It's commutative, but only in the format. This thing, you can, if you put a bracket around this guy, you can't put a thing. You can only commute pair matrices, two matrices past each other. You can't commute a triple of matrices past each other. It's not commutative. It's got this funny property where you can switch up two matrices in trace. Okay, this is kind of weird. Okay, also it's not multiplicative. Okay, so let's do the counterexamples. Let's do the trace. Let's do I'm gonna let A be 1, 1, 0, 1, and then I'll put B as 0, 1, 1, 0, and C as 1, 1, 1, 0. Okay, so if I multiply these together, I get 1, 1, 0, 1 times, so multiplying this is going to be here is going to be 1, 0, 1, 1, and this is going to give me 2, 1, 1, 1. Okay, cool. So the trace of this top one is 3. So trace of A, B, C is equal to 3. Okay, so let's do it the other way. So let's do it like so. This is my A, this is my B, this is my C. Let's do ACB. Okay, 1, 1, 0, 1 by 1, 1, 1, 0 and 1, 0, 1, 1, 0. If you go through this thing, you get that this is equal to 2, 1, 1, 0. So the trace of A, C, B is equal to 2. So they're not equal. Okay, so you can rotate entries through each other. So you can have trace A, B, C. This is equal to the trace. So I'm pushing the C to the front, C, A, B. Okay, now I'm going to push the B to the front, trace B, C, A. Okay, and then I can push the A to the front to go back. Okay, so the trace is a little bit different to what you're used to. So the trace handles similar matrices. So basically the way you prove this is, well, if you let A be a similar matrix, so A, the trace of A, well, this is going to be equal to the trace of S, B, S inverse. Well, I can rotate this. So I'm going to put this group of matrices in the front. This is B, trace of B, S inverse S, which is just going to be the trace B. Cool. And we already know this part, so we've got that one. So we've just proven this. So the trace respects similar matrices. Cool. So we know it's a fundamental property of linear algebra because it respects similar matrices. Okay. The determinant in trace. So it respects similar matrices. So the trace of A. Okay. The way you prove this is a little bit funny. The trace of A is equal to, if A is diagonalizable, the trace of D, where D diagonal with entries lambda 1 through lambda n. Okay, but we know that matrices aren't in general diagonalizable. We can't in general take the find the diagonalization. Okay, so and this also gives us the determinant of A is equal to the determinant of D. Okay, and now these two parts I can compute. This is the sum of lambda i's, and this is equal to the product of lambda i's. So we get that these two formulas are true for diagonal matrices. Now if you're not diagonal, if you can't diagonalize, well, what you can do is you can put it into Jordan canonical form. Now what you may ask about Jordan canonical form is, what is it? And Jordan canonical form is something you can always do to matrices, and it handles the ability that to have basically it allows you to build a kind of a diagonal matrix. It's close to a diagonal matrix. It works just like a diagonal matrix. It's upper triangular, and it's got the eigenvalues along the diagonal, and then just ones above the diagonal in certain places to make it work out. Okay? Jordan canonical form is a little bit more difficult than diagonalization, so we're not going to get into it. It's just not necessary for our purposes. So you can prove this in general using Jordan canonical form. So in general, since we got this, the trace and the characteristic polynomial. So supposing A is diagonalizable, we can do say some things about the trace. Okay. So the trace of A is going to be this component. Okay. So we know. Let's just write this out. A11, A12, A21, A22. Okay. So if I'm taking the determinant, I'm going to subtract lambda from this and take the determinant. So this is going to be equal to the determinant. This is going to be equal to A11 minus lambda, A22 minus lambda, minus A21, A12. Okay, so if I product this all out, this is equal to lambda squared minus, okay, A11 plus A22. Okay, that's the trace. Lambda plus A11 A22 minus A21 A12. Okay, so in general you can't you can write this all out in terms of trace and determinant only. You can do the whole thing, but that doesn't help us much because it's a complicated ass formula, and you just go through and do the determinant. It's much simpler. But we always know, okay, but we always get, so for an n by n matrix, a n by n, the characteristic polynomial of A, okay, characteristic polynomial of A is going to be of the form lambda, negative lambda to the n, okay, plus negative 1 to the n minus 1 times the trace of A times lambda to the n minus 1. So I know what the second term of my polynomial is. I got this thing is going to have a negative sign depending on this n. This is going to have the trace with a negative sign depending on the n. Okay, so I always know that. And then the hard stuff, the stuff that I can't compute, but that always ends in the determinant of A. Okay, it always ends in the determinant of A, and the second term is always the trace of A. So once we got that, we can check our polynomial. We can use this as an error checking device, but it is just an error checking device for a 3 and higher order matrix. So if you have a 3 by 3, a 4 by 4, 5 by 5, there's nothing you can use to do this that is you're going to remember. Okay, I can give you the formula for a 3 by 3 and a 4 by 4, but it's complicated and you won't remember it. Okay, just do it. But if you're doing the problem, just check the trace and the determinant, and if you got the trace wrong and the determinant wrong, well, it'll screw you up. Okay, you can double check. This is a way of double checking your characteristic polynomial before you go through and find the eigenvectors. Okay, so thank you very much for listening to me.